Okay. So now we get to the idea we need a very simple picture, and we're going to conserve angular momentum. What is it? Whatever. So concerned with changes in v. So every equation we write down has to be in terms of that v, that absolute. Hopefully, I gave enough physical reasoning as to why it should be v, why you draw these vector things, but just take it on the chin that it should be that v, not the u, not the w. Okay. So what conservation equation we have? We have in the control volume sense, we have to say this. Dot n. Right? This is conservation of angular momentum, and that is the sum of the external torques is that equal? So always for engineering, you do these control volume things, and I'll draw it later again, but that's the conservation equation we're getting at. This is also steady state. Why? Because there was no DT part there. So every class you just say it's steady state. But the idea that you have a sum of the torques, it's just is now the flux of the momentum across the control surfaces for this simple impeller diagram. Okay, so there's a dn there, right? So we should, right, this is respect to like orthogonal coordinates, so we'll have to maybe break this velocity vector up into those two terms. This will result in a torque. So these are just the torques. That's this idea of, think of it on this side, plug it, right? This is the idea of you plugging it into the wall, and this is the effect of plugging it into the wall, okay? Forces prescribed motion. Okay, so that's the equation you write out. But you can kind of sort of graphically solve these things. Maybe I'll just stick to my notes. Something like this. So if this is my surface, right, the surface being, right, you orient a normal vector to that surface outward normal, right? Clear, right, some good coordinates are the radial system, right? If it's a radial system, that would mean that the normal vector is equal to one of your, right, is equal to one of your principal axes of your coordinate system. Makes things nicer. This is the boundary. Okay. So then what else do we have? So then whatever it is, whatever it ends up being, right, is you'll have that, right, that net velocity vector will have components, right, and components being little v, right? This is the radial one. I've just scaled by the r that it's at. Sometimes there's a 1 over r embedded in here. You can also just, right, I just have it in the r there as well. So these are now components based on that, right? You can see that the u here is clearly some scaled up version of this vector, whatever it ends up being. If you remember what that u was, it's going to be unscaled on this. And then this is some, right, you don't, right, and then w and, right, then w and v are sort of going to be, they have components based on this n right here. But, right, u is definitely, right, totally just a scale version of this e theta vector, right? The ER vector is the normal vector in this coordinate system, right? You have to imagine this is, here's the hub, so this is all spinning this way. That's my blade. Okay, so in terms of fluxes, right, the dot n in that last equation, that's where that comes into play, right? So what do we have next? Then other terms we have to talk about, well, there's this R cross F. What do we have there? That's going to end up just being a torque. And what is that component? That's actually in the z direction, right? I have, in cylindrical coordinates, I have component in the r, component in the theta version, and this is the coordinate for the z direction. You should all remember that torques are in the direction of the rotation, right-hand rule, boop. So this is just some scalar value of power or force, right? From a scalar value of a torque that you've applied. What's the other term that we had in that equation? We have this one. Okay. Show that, right? Show that based on this, apply the cross product, extra credit, boom. Simple, but you'll see how cross products behave that way. And you should get a sense that that's always the case if you have a cross product, right? This is the R going this way and then the velocity this way. So cross products should always be thought of that they produce a vector that's in the perpendicular plane. So just looking at this term, I would see a radius vector going out this way. I would see maybe some velocity vector that way. I would know that it's going to be either in or out. So you can show it graphically, but calculate this actually using a cross product. It's not that bad. Okay, so those are the terms, enough terms to write something down now. Referencing back to that conservation equation, right? What are you going to have? After you do all these things, you just get components in this. This is all that matters in that equation. Reference a book, look it up in the book. I think it's important to do that. So all those terms break down, you end up just getting an R, or sort of in one row, a negative velocity. Okay. Right? This negative came from the fact that my inward normal on the inside was at their opposite direction. So that gives you a -1 right there. So that's going to be where that comes from. But it's just the same thing as projecting areas and calculating these things. The rho came from the integral side on the right-hand side. You only had inward fluxing, you only had influxing area and outfluxing area. So there's actually pi's and r's based in here. You don't need to write them down because it doesn't matter. But same process of this control volume of flux across the surface, outflux across the surface. This negative comes because of those different, because of the opposite directions on the normal vector versus where the fluid's moving. Okay. What do you have? You just have now. Okay, yeah. Collect terms. Boom. Boom. And this is just changing the terms around. I have a negative sign out there now. And what do you have here? Well, this is a mass flow rate in. This is a mass flow rate out. Conservation of mass says those are the same, so you can factor it out. They just equal one mass flow rate. Okay? Then next step is you get the Euler old man equation of turbo machines or something. And here's sort of our first step along the road to quantifying the effects of a turbo machine is this relationship. say is you get this idea that after you drew the simple enough project and the simple enough picture you could have, you would just have my applied torque has to equal the mass flow rate of the system times swirl outward velocity, swirl inward velocity. It's a difference of these things. It's not too hard to understand where these quantities would come into play because torque is the net change in angular momentum, which is what you've written here. Same as force is the net change in linear momentum. You just wouldn't have angular components in there. So a difference like this is still saying a change in angular momentum. You could show that. Okay, we're on our way even more. So this is kind of useless in reality because if you imagine applying a torque, right? I mean, I think they're difficult to measure, especially in terms of plugging something in. So what we usually do is we talk about the power of the shaft. When I was in class, I literally could not stop laughing when someone said the power of the shaft. Okay, so you just multiply the rates, right? Just as power was a force times a velocity, rotational shaft power is still the same thing. It's a torque times an angular velocity. So not too hard to understand, I don't think, on that one. Okay, so you multiply this entire equation by that. What does that do, though? It does something pretty neat. Okay, so if I take that shaft equation, and now I have this on the right, okay, multiply through by the omega, I'll keep this mass flow rate, I'll have omega u. Okay. Oh, sorry, I jumped the gun on that. Right, I just multiplied through by the omega, and that's what I was trying to get at, jump the gun, right? There's this cool thing that you just do that, and you go, hey, look at that. Those were those, right, tangential radial velocities that I had before, right? This is just going to be the scalar component of u2, scalar component of u1, right? That's pretty cool. I think it's cool. So then what you're going to get is now, if you divide by the mass flow rate, you'll get something called specific shaft power. So this is an even better result because now I just kind of see the balance of two velocity vectors I had before. And this is a component, right? These are the component scale values, and this is something. So combination now I can see of this velocity I'm trying to get at versus this radial one that you can get just from an angular velocity. So we're in a better setup now to maybe estimate powers because I can get a handle on more of these values than I could before. Okay, so next we'll use the actual velocity triangle to simplify this even further.